Hello, I'm Marco, and in this video I'm going to tell you about Claycode, our journal paper at SIGGRAPH 2025 by Alberto Crescini, Marco Perronet, Elena Camuffo, and myself. So Claycode is a new type of scannable code. You can think of it just like QR codes, but instead of encoding data in a matrix of black and white, it uses trees, and in particular encodes data as a nesting of color shapes one inside the other. This enables a whole new set of features, first of which Claycodes are deformable. So that means that they can be fit into any shape. Here you see some examples, even extreme. And also that they are basically immune to all the plastic deformations that you see in everyday life. The other important thing is that Claycodes are very stylable. You can change the style of your codes without changing the scanner or the underlying technology. Here on the left, you see some examples where this is done with traditional code, and also some examples of companies making their own codes just to have their own style. Taking this one step further, you can also animate these codes. Here you see two examples. This is how much we explore so far. But you can think that as long as you don't break the topology, you can do pretty much whatever your fantasy tells you. In this paper, we talk about the whole pipeline. This whole thing is implemented and is available online. Check out the generator at claycode.io. There is also a scanner implemented as a web app at claycode.io/scan. You can also find the code online. Let's talk about each component of this pipeline. So first of all, we need a way to map bits to trees. This is not really rocket science. It has been done in the past. However, here we have a specific problem and specific requirements. First of all, we want to pack as much information as possible in a given topology. Second, we intuitively want longer messages to map to more complicated codes. And third, the encode-decode procedure must take at most milliseconds. It's important for our paper to define what a complicated topology even means. Intuitively, you might think that a complicated topology is one that has many nodes. This turns out not to be the case. In the example here, you see on the left a Claycode that has 30 nodes, and on the right, one that has 150. However, they take up the same amount of space while being roughly at the same level of readability. To describe this mathematically, we have created a metric we call footprint. It is very simple. The footprint of a single node of a tree is just 1 plus the total number of descendants of the tree. And the footprint of the entire code is just the sum of the footprints of each single node. It is not super important to deeply understand this formula. What's important to know is that it scales quadratically with the height of the tree. And the height of the tree is what makes drawing it so complicated. So let's now talk about our bit-to-tree encoding, the first element of our pipeline. We have searched the literature for an encoding that satisfied our needs, and we really haven't found one, but we got close. There is a paper from 1994 that satisfies most of our needs, but sadly it uses factorization, so it's not really practical to implement on a smartphone. So what we have done is that we have devised a new encoding, similar in spirit. Our encoding is based on seeing the string as a natural number, and then recursively subdividing that number into a sum of squares using a greedy strategy. This is super fast to compute, and it yields comparable results that you can see on the top right. During the development of this paper, we have tested a variety of encodings and finally selected the one that struck the best balance of speed, efficiency, and simplicity. The second part of our pipeline is what we call the packer. Now, the packer is the component that draws the Claycode starting from the tree. At the bottom, you see a representation of what the packer algorithm should do. And you can see that the final result is a code that contains exactly that topology and also is drawn in such a way that nothing is too thin and no element is bigger than it needs to be. In our implementation of the packer, we combine two fundamental operations, padding and partitioning, into a recursive algorithm. We process nodes one by one, and for each node, we first pad some space in the available polygon to make some space for the node we are currently processing, and then we partition the remaining space among the children of that node. Padding is a pretty standard geometrical operation that we use largely unmodified in our paper. However, partitioning is much more complicated in general as a problem. In fact, many formulations of it are non-polynomial. In our paper, we solved this problem guided by two main heuristics. One is called area proportionality, and it's quite intuitive. Basically, every sibling should get an amount of area proportional to its footprint. And the second one, maybe less intuitive, is circularity, which should favor solution with compact polygons. We linearly combine the two to form our minimization problem. Now, intuitively, you can see what happens if you skip one of these two. So on the left, for example, you see a solution that has good circularity, so shapes are not too long or too thin. However, it doesn't have good area proportionality. You can see that one of the nodes is taking a disproportionate amount of space, cramming the remaining ones into a small area, and making it harder in the future for a scanner to figure out the exact topology. In the center, you see the opposite. Area is distributed correctly, however, the shapes are not very circular, and hence, again, the scanner will have a hard time. Finally, on the right, you see the correct and intuitive solution where the two heuristics are combined in the right way. So here you see some examples of the packer in action. Everything you see has been generated with this algorithm. And on the top left, you even see the algorithm running. This is real time and it's unmodified. So if you go on claycode.io, you can see it working in the exact same way. Finally, let's talk about the last element of our pipeline, the scanner. This is another whole challenge. In fact, we cannot rely on markers or visual cues or even a fixed shape like we usually do with other scannable code. However, at the same time, we do not need to worry about distortion because of perspective, because of lens, or because of plastic deformations. In fact, the very same problem of not knowing the shape turns into a feature because you don't have to correct for such things. So how do we solve this problem? In the paper, we show how we flip the script and instead of first trying to find the code, isolate it, and then decode it, we turn the entire scene into a topology tree first. And then we work on the topology tree to figure out where the code is. Intuitively, in the given example here, you see where the code starts because you see this vertical stack of nodes. However, we need something much smarter for real-life applications with complicated lighting and noise. What we do is we first build a list of possible candidate trees that could be Claycodes, starting from the global topology tree. Now, you might think these will be hundreds of thousands, but actually, if you use some very simple heuristics, like eliminating the trees that are too small to possibly contain a message, you actually eliminate already 99.9% of the candidates. So what you can do here is turn all of those trees into a message using our bit-to-tree decoder we explored earlier. And what you're left with is a series of messages, some of which will be noise, most of them, and one or possibly more would be an actual Claycode. How do you distinguish between them? Well, at code creation time, we append a cyclic redundancy code, or CRC, to each generated message. This is a technique used, for example, in network stacks to identify errors. Here, we're using it to distinguish noise and messages. In short, we start with the global topology tree of the entire scene. We build a list of candidates, eliminating 99.9% of trees that could not possibly contain a message. We translate all of those trees into strings of bits. And finally, we apply our CRC check to identify where the real Claycode is or are. A good feature that counts for free here is that we can scan multiple codes at the same time with the same pass. This is a feature that we actually use in the paper to build some error tolerance system. Here you can see some examples of the pipeline working in real time on a regular smartphone. We're scanning a heavily stylized code in a real environment with complicated lighting, some occlusion coming from the glass bottle, and also some distortion that this bottle imposes on the code. On the right, you see a similar setup where instead we are decoding a code that is digitally stretched to very high degrees. We were actually surprised ourselves to see that it works even in such extreme situations. Again, you can try this if you want. You just have to go on claycode.io/scan, and hopefully you will be able to use a web app that does just the same. In the paper, we explore the capabilities of Claycodes in depth, both in a very controlled scenario where codes are projected on a screen with a fixed amount of deformation and occlusion, and in real-life setups like the ones you see in the video there. What we found is that Claycodes are superior to barcodes and QR codes in tolerating distortions. You can see that the success rate here at the top basically doesn't go down no matter how much distortion you apply to them. When it comes about occlusion, Claycodes are competitive, but much more in line with QR codes. That was our paper. Thank you very much. You can find all of the code online. You can find the scanner at claycode.io/scan and the generator at justclaycode.io. And for anything, please leave a comment or write us an email. Thank you very much.